In this section and in the next section, we begin to do a lot more heavy stuff with fractions. And to sort of get an idea of where we're going, I want to draw some pictures. So these are supposed to be equal squares. I'm dividing it up into 9 places. And then what I'm going to do is take another one just like it. So what I have drawn here is on the left, this left square, only 1 out of 9 of the squares are shaded in. And on the other one, only 4 out of 9 of those are shaded in. Now, if I go ahead and push these together, so sort of kind of merge them into one square, I guess you could think of them as overlaying on top of each other, whatever way you need to think of it. It doesn't matter to me. But when I put them together, I'm going to get that top left one, and then I'm going to get these bottom ones from the other square. So if you look, we have a total of 5 squares shaded in all. So it's easy to see that when I did 1/9 plus 4/9 equals, I added the 1 and the 4. If you look, I added the squares. Look over here, the 1 square from the left and then the 4 squares from the right. I put them together and I added them to get a total of 5 of them. So we got 5 out of 9. Well, this seems simple. We have exactly one rule that it involves the addition of fractions, and that rule looks like this. If I have a fraction and I'm adding it to another fraction, but the key is they have the same denominators. You see they're both over b. I simply add the numerators together and the denominator stays the same. So this rule here is called the addition rule. And I don't have to go, I'm sure I don't have to do a lot to explain that the subtraction rule works exactly the same. As long as they have the same denominator, I can do this. So let me go ahead and square this off because that's important. One rule is all we have, but yet you won't believe how complicated this gets. So I'm going to do several examples, easy examples at first, and then I'm going to move on. So let's go with an example. I have 3/7 plus 1/7, and then when I add them together, I do 3 plus 1 over 7, and that's equal to 4 over 7. Similarly, if I do 1/10 plus 3/10, I get 1 plus 3 over 10. That's 4 over 10. But now, if you were asked to simplify the answer, notice that I can cancel out a 2 in both the 4 and the 10 and get 2 over 5. So even though you can add them up, they still may need to be simplified when all is said and done. Another example, 14 over 15 minus 7 over 15. That's going to equal 14 minus 7 over 15, which is a total of 7 over 15. And I can't simplify that one. Then we have 11 over 14 minus 5 over 14. That equals 11 minus 5 over 14. So the denominator stays the same, of course, until I do some simplifying if need be. 11 minus 5 is 6, so I get 6 over 14. And then once again, I can divide out a 2, and I'll get 3 over 7. And it's just a matter of doing more examples and showing you little bits and details that you'll come across as you do these problems. So here I got negative 20 over 13 plus negative 6 over 13. The way I think of it is you probably would want to think of it this way. I'll put the negative attached to the 20. Remember, you can put the negative anywhere you want, in the top, in front, or underneath. But I think it'll be a little more helpful if I do it this way. This way, when you add them together, you'll be dealing with the type of stuff you've seen before. And then negative 20 plus negative 6 is negative 26. And here, 13 goes into 26 twice, so this simply equals negative 2. Let me do another one. Here I have 3/8 minus 5/8, and that's equal to 3 minus 5 over 8, which is negative 2/8. And once again, I can simplify. 2 goes into both of those numbers, so I'll end up with negative 1/4. And then we could do something like this. Next example, suppose I have 6 over 28 plus 17 over 28 plus 5 over 28. Well, I just add up all the stuff in the numerator. I'll get 6 plus 17 plus 5. All of that will be over 28. And I believe that's 28. 28 over 28, well, that just equals 1. Next, suppose I have 3 over 11r plus 7 over 11r. Since they both have the same denominator, I can just add them together. 3 plus 7 divided by 11r, and that's 10 divided by 11r. Since 11 is a prime number, I really can't do any simplifying there. And then we have 4 over 7k minus 2 over 7k. That's going to be 4 minus 2 divided by 7k. And that equals 2 divided by 7k. So even though the letters there, they don't complicate things because we have the same denominators. By the way, your textbook uses the phrase, when two fractions have the same denominator, the book refers to them as like fractions. Next, I have 13 over 18x minus 7 over 18x. And that's 13 minus 7 over 18x. That is not 6x, but just 6 over 18x. And this one can actually be simplified. 6 goes into 18 3 times. So this equals 1 over 3x. I'm just trying to do a little bit of every kind of problem you might come across. Next, I have the letter m over 5 plus 2 over 5. There's not a lot here I can do. I can just add the two numerators together, And that's it, because I don't know what m is. I can't combine anything. I can't simplify anything until I know what m is. So I'm done. Now, that takes care of all the situations where we have similar denominators. The same denominator, in fact. Now, what do we do for something like this? 7 out of 10 plus 8 out of 15. How do you work something like that? Well, before I answer that question, what I'll do is do a little bit of work trying to show you how to get the denominators to be the same. I can't, the rules that we have right now will not allow me to add these two fractions together just yet. So I need to take a little detour for a moment and explain some things first, and then we can come back to this type of problem. So from now on, I'm going to use a 3-letter acronym. LCM means least common multiple. And let me do an example to show you. I want to compute the LCM of 10 and 15. That means what I want to do is find the lowest or the least common multiple of these two numbers. So let me write some things down here. Let me start with the multiples of 10. This is where you start taking the number 10 and you multiply it by whole numbers. So, for example, the first multiple of 10 is 1 times 10. The second multiple is 2 times 10. The third multiple is 3 times 10. And hopefully by now you get the idea. There's the 7th multiple, the 8th multiple, the 9th multiple, the 10th multiple, and they go on forever. You can keep doing this for eternity. Now let me also look at the multiples of 15. So I'll start. 1 times 15 is 15. 2 times 15 is 30. 3 times 15 is 45. So basically you're counting by 15s. And these also go on forever. So if you look, they have multiples in common, like they both have a 30. Let's see what else. They both have a 60. They both have a 90. And of course, this can go on forever and ever. So all of those that I circled are common multiples. The lowest common multiple is the smallest of these. So the LCM is the least of those common multiples. So that's 30. That's one way to do this. Let me try another example. Let me circle this to let you know that this problem is finished. I did what was asked of me. Compute the LCM of 6 and 8. So I'll play the same game I did before. I'll look at the multiples of 6. So I have 6, basically count by 6s. So I'll stop there because I think I'm going to have enough there. And then the multiples of 8 I'll count by 8s. And this goes on forever as well. What I now want is to find common multiples. So if I look along the 6, I notice that there's a 24 here, and there's a 24 for the 8 as well. And since it's the first ones that I circle, that is the LCM. The LCM equals 24. Notice that they did have other multiples. For example, I think we had another one at 48. They both had a 48, but those, of course, are not the lowest or the least common multiples. Let's do another one. Compute the LCM of 45 and 54. So let me start with the multiples of 45. So I'm going to count by 45s. So 45, 90, 135, 180, 225, 270, 315, 360, and this goes on forever. I hope I have enough. Now the multiples of 54. So I'll count by 54s. So 54, 108, 162, 216, 270, and I'll stop there because I noticed that 270 was also on the other list. This was the first time I saw that they had a common multiple, and that was at 270. So the LCM equals 270. One last example. I want to compute the LCM of 72 and 125. So let me look at the multiples of 72. So I'll count by 72. So I have 72, 144, 216, 288. That's for 5 times, that's 360. It's easier for me to multiply. 6 times 72 is 432. And then I believe I have a 504. Then I have a 576. And this goes on. And then the multiples of 125. I'll start with 125, 250, 375, 500. So far I do not have any multiples in common. 625. I've now, my list for the 125 is bigger than the 72. I still don't have anything in common. So what you could do is keep extending this, I guess. I could do 750 here, and then after 576, if I add 72 to that, would be 648, and then add 72 again would be 720, and The next one after that would be 792. If I do it again, that would be 864. Well, let me add to this one here. 750 plus 125 is 875. Well, the thing is, this goes on forever. Let me show you. Actually, the point of this example here is that this method where you count up the multiples may not always be the best way to do it, because as this goes on, guess what? They don't have a common multiple all the way until 9,000. So the LCM, the point I'm making is that doing it by counting multiples, while it will work for probably small numbers, for general fractions with different denominators, you're probably going to want to come up with a different and better method of doing it. And that's the whole point of this exercise. So here's how we do it. Start with 72, and I'm going to make a factor tree. Now give me the smallest number that goes into 72, besides 1, of course, 2, and that also happens to be a prime number, and it goes into there 36 times. I'm going to continue. 36 is 2 times 18. 18 is 2 times 9. And then 9 is 3 times 3. So if you recall, that means that 72 equals, when I look at my 2's, I have 1, 2, 3, and then I have 3 2's. So I have 2 to the third power times 3 to the second power. Let me do the same with 125. Well, the only number I know for sure that goes into 125 is 5. That's 5 times 125. I'm sorry, 5 times just 25. 25 can be broken down as to 5 times 5. So 125 is simply equal to 5 to the third power. So now here's how we make the LCD, or the LCM. Actually, the LCM and the LCD that I'll get to are the same thing, but I digress. LCM equals. Here's what you do. Look at all the prime numbers that are involved in this, in all the numbers. To make up 72, I used 2's and 3's. To make up 125, I used a 5. So for my LCM, what I'm going to do is put all of those prime numbers like so. My next task is to figure out the exponents. So if you think about this, you know, the LCM is a number that 72 goes into it evenly, and 125 also goes into it evenly. In order for 72 to go into this thing, I need at least 2 to the third power, or 72 doesn't have a chance of going into it. So I'll put a 3 up there. Next, I'll also need 3 squared, since anything less than that will not allow 72 to go into this thing. And then finally, I'll need 5 to the third power for the 125 to go in. And then when you multiply this all out, I get 8 times 9 times 125, and I think that that is 9,000. So the way we build this is we use all the prime numbers that are involved. How we choose the exponents is we look across, and when I look at all of my exponents that involve 2, I want to pick those with the highest exponent. All of those numbers that deal with 3, I want to pick the highest exponents, and 5, I'll do the same thing. This had an example where these numbers did not break down in a way that they shared any common factors. So that is one of the reasons why the number 9,000 was so big. So this is the way I prefer to do it. on bigger numbers. I'm going to redo a previous example next. Compute the LCM of 45 and 54. So this time I'm going to use this new method, using a factor tree and then creating an LCM based on the prime factors. So let me start with 45, and I'll break that down. Notice the 2 doesn't go into it, so I don't have that going for me. But if I take 4 plus 5, that's 9. That means both 3 and 9 go into 45. I always pick the smallest possible number that goes into this thing besides the number 1, and the smallest number then will be 3. I'll circle it because it's a prime number. 3 goes into 45 15 times. 15 can be broken down. And then all these circled numbers are the prime numbers that make up 45. So accordingly, 45 equals 3 squared times 5. That's of course because you see 3 2's and only 1 5. For this process, you may want to put a 1 there because it'll help you count how much exponent there is on that number. Let me go to 54. This time it is an even number, so I will factor out a 2, and that leaves me with 27. 27 is not prime. If you take 2 plus 7, that's 9, so I know that both 9 and 3 go into 27. And then the 9 breaks down as 3 times 3. So the 54, this time I only have 1 2, but I have 3 to the 3rd power. So I have 2 to the 1 times 3 to the 3rd. Now comes the construction of the LCM. Let's look at all the primes that we have. I've got a 3, a 5, a 2, and a 2. So 2, 3, and 5 are all the primes. So I've got a 2, a 3, and a 5. Now I just need to figure out the exponents. As you look through all the numbers, start with 2. What is the highest exponent you see on 2 in all of these numbers? Well, I only see it one time, and it's only to the 1st power. So that's all I'm going to need. Next, look at 3. If I look at all the exponents, here I have 3 squared, here I have 3 to the 3rd. I want the one with the higher exponent, so I'm going to write 3 to the 3rd. And finally, I only see 5 in one spot, and it's to the 1 power. So when I multiply this out, I believe I get 270. Which, once again, we got earlier in a different manner. There's another way that you can see this. In this previous example, I have an LCM of 2 times 3 to the 3rd times 5. Look at 45. 45 was equal to 3 squared times 5. If you look here, look at this. I'm going to rewrite this in a separate way. You see it right there? There's 45. It's inside of this number if I break that up in a certain way. Right there is the 45. So you can see that 45 goes into the LCM. However, 54 was equal to 2 times 3 to the 3rd power. So if I look at the LCM in a slightly different way this time, you can see it's built into it. Right there, 3 to the 3rd times 2 is 54. So you can see 54 goes into the LCM also. So both the 54 and the 45 go into my LCM. So they are, in fact, factors of this number. Let's do one more example. Compute the LCM of 180 and 245. I'll start with 180. That's 2 times 90, and I'll circle the 2. 90 is 2 times 45, and I'll circle the 2. Now the 45, I can't pull a 2 out of it, but I can pull a 3 out of it, because 4 plus 5 is 9, and 3 goes into 9. And I like pulling out a 3 because it's a prime. And then I can break the 15 down. Got it. So 180 equals, let's see what we have here. I've got 2 2s and 3 3s. So I got 2 to the second. I don't know why I said that. I have 2 2s and 2 3s plus a 1 5. So I got 2 to the second, 3 to the second, times 5 to the 1. Now let's look at 245. I'm going to see if I add these digits up. 2 plus 4 is 6, plus 5 more is 11, and neither 3 nor 9 go into 11, so you can forget about 3 going into this. It's an odd number, so I was trying to see if 3 went into it. However, I notice it does end in a 5. That means I do know that 5 goes into it. And 5 is a prime number, so we're still getting somewhere. I think that's 5 times 49. And then 49 is 7 times 7. So we have 245 equals 5 to the 1 times 7 to the second. When I make up my LCM, I'm going to want to list all the primes that are involved. And what do I have? I have 2, I have 3, I have 5, and I have 7. So 2 times 3 times 5 times 7. Now I just have to figure out the exponents. The highest exponent on 2 anywhere that I see is a 2, so I need to have 2 to the second power. Now the highest exponent I see on 3 anywhere is this 3 to the second. I only need 5 to the 1 because the highest exponent I see is a 1. And then I need a 2 for my exponent on 7. So we have 4 times 9 times 5 times 49. And if I did my multiplication correctly, this is 8,820. And so that takes care of the setup for what is really the homework, or the gist of what I'm getting at is in section 3.5. Now we are going to add, subtract, unlike fractions. These are fractions with different denominators. So once again, let me remind you of the one rule that we have. So all we have really is one rule, and it involves having common denominators. If the denominators are not the same, then we have to do something to make the denominators the same. That's why I only have the one rule for the multiplication, or I'm sorry, only one rule for addition and subtraction, is because we're going to be given fractions with different denominators, and we are going to make them look like this. So let me write this. I don't know how big I need to write this, or how much you need to know, but let me even use a different color ink because this is so important. Let's choose red. So we can only add / subtract fractions that have the same denominator. Never forget that. That is what we're always going to be working at, is trying to get a common denominator, in fact, is what we're going to be doing. So let's start with a simple example. All right, so what I want to do is add 1/3 plus 1/5. As it stands, I can't add these things together because they do not have the same denominator. I plan on making the denominators the same. Remember this trick. If I had a times a number and b times the same number, I could cancel out that x and get a over b. Well, there's no reason I can't go in the reverse direction. So example, like I want to do this. I want to multiply the same thing in the numerator and denominator for each fraction and arrive at numbers that are the same for the denominator. So for example, what I need to do is figure out the LCD. Well, guess what? The LCD, which is, by the way, lowest or the least common denominator, LCD is the same as the LCM. So LCD means least common denominator. So what we've been doing has been constructing these LCMs, or LCDs as we now know them, and I'm trying to figure out what that is. So the LCD equals 3 to the 1 times 5 to the 1. Since I'm trying to figure out the LCD of a 3 and a 5, this number here, this 3, is just like 3 to the 1. There's no breaking it down. And this 5 is like 5 to the 1. So in order for both of these numbers to go into this LCD, I need to take them each to the highest power that they appear in, and that's only 1. So I need to construct an LCD of 15. So here's how we do it. We know, the whole point of LCD is we know that 3 and 5 both go into 15. How many times does 3 go into 15? It goes in 5 times. But whatever you multiply in the denominator, you have to do the same in the numerator. How many times does 5 go into 15? Well, it goes in 3 times. But whatever you do in the denominator, you have to do in the numerator. So that changes these fractions now. Now I have 5 over 15 plus 3 over 15, and that equals 8 over 15. Let me draw some pictures. So this picture here can be thought of as 1/3. For my next picture, what I'm going to do is this. I think I have, well, let me fix this side up a little bit, and just so I make them all so they look the same. There's 1/5. Now, what I did here is I turned the denominators into 15. So what I can do, watch this. If I take the 1/3 and I add 4 lines in it, if you look, I now have 15 little rectangles or squares there, right? And we can see that there's 5 of them. Additionally, if I take the 1/5 and I break it up into thirds like this, I take the whole thing and break it up into thirds, that's 15 rectangles again, but this time I have 3 of them shaded. And then once you get to that stage and they have the same denominator, you can, of course, add them together because the denominator is the same. So that's the game that we're going to be playing for all of these. So I'm going to try to develop a method that after a while will seem like it's not as bad as it seems now. Will seem less daunting. Will seem more natural. Let's do another example. And the only way you can really do that is by doing a lot of examples. So I'm going to do 1/6 plus 7/18. And I want to know what the LCD is. Well, if you look, 6 is equal to 2 times 3, and 18 is equal to 2 times the 3 to the 2nd power. You can do a factor tree for these to verify these numbers that I'm getting. But when I make up my LCD then, it's going to only involve a 2 and a 3 because those are the only numbers, the only prime numbers that are in these breakdowns. Notice if I look at 2, the highest power that you see anywhere on 2 is to the 1 power, so that's all I will need there. The highest power of the 3's that you see anywhere is this 2, so I'll need it to the 2nd power, and that equals 18. Now, you watching me do this, you may have known that 18 was going to be the LCD, but I wanted to stick to the method to show you that it always works. That means I can leave the 7/18 alone, but I want to change the first fraction to have a new denominator of 18. So let's look at this. If I take 6, how many times does it go into 18? Well, 18 divided by 6 is 3. So I multiplied 6 by 3 to make that into 18. I also have to multiply the numerator by 3 to make it into 18. And just so I'm not seeming to skip details, let me do this so you can see where it comes from. I multiplied the numerator and denominator by 3. So you get 3/18 plus 7/18. That's 10/18. So I can cancel out a 2. And I'm left with 5/9. So some of these will require a little bit more effort. It all depends on the numbers. Let's do another example. Here I'm going to do 3/8 plus 35/56. And once again, I'm going to break down these numbers, and if you need them broken down and you need to see how they break down, go pause the video and do a factor tree. Do 2 factor trees, in fact. But I'm going to write this for now. 8 is equal to 2 to the 3rd power, and 56 is 2 to the 3rd power times 7. So when I create my LCD, I'm going to need a 2 and a 7. Those are the prime numbers that are involved. And then as I look at the exponents, the highest exponent for 2 is a 3. Similarly, the highest exponent for 7 is a 1. And that equals 56. So I can leave the 1 as fine as it is. All right, so what did we have to multiply 8 by in order to turn it into 56? We need to multiply 8 by 7. And then whatever I do to the denominator, I do to the numerator. So I get 21 over 56 plus 35 over 56. Oh, well, this is nice. This equals 56 over 56, which equals 1. By the way, this problem could have been done a lot easier than what I just did. Although I don't want you to think that this example is a bad example. Sometimes if you're on your toes, you can see that you can simplify one of the fractions. For example, the 35 over 56, 7 goes into that. So I could have, instead of by doing what I did before, I could have simplified one fraction and gotten this. 3/8 plus 5/8, that is 8/8, which is 1. So a lot of times there's more than one way to do one of these things. Let's try a negative number. Negative 2/9 plus 1/6. These are easy numbers to break down. 9 equals 3 to the second, and 6 equals 2 times 3. So when I create my LCD, I'll need a 2 and I'll need a 3. But then when I look through my exponents, the highest exponent on a 2 is 2 to the 1, and the highest exponent on a 3 is 3 to the second. So this equals 18. So my LCD is 18. So what I need to try to do is get each of these to be over 18. So I need 6 times what, and I need 9 times what. I'll put the negative up there with the 2. That's usually beneficial. Ask yourself, how many times does 9 go into 18? It goes in twice. And then whatever you do down there, you repeat in the numerator. 6 goes into 18 3 times. But whatever you do down there, you got to do in the numerator. So I have negative 4 over 18 plus 3 over 18. When I add them together, I get negative 4 plus 3 over 18. And that's negative 1 over 18. As I mentioned, I don't know if I ever wrote this or not. No matter where you put the negative, you can put it where it's most advantageous for you if you would like. All of these things are the same negative number. No matter if the negative is attached to the top, the middle, or the bottom, it's the same answer either way you slice it. Next, let's do 9/10 plus negative 11 over 15. If I take the 10 and break it down, it's 2 times 5. If I take the 15 and break it down, it's 3 times 5. So when I create my LCD, I'll need a 2, I'll need a 3, and I'll need a 5. The highest exponent I see anywhere on all of these numbers is to the first power. So I don't have to write the exponent if I don't want, because it's assumed. I think this turns out to be 30. So what we want to do is I want a 30 in the denominator for each of these. So this is the way I typically do these problems. Start with the first fraction. What did I multiply 10 by in order to give me 30? I had to multiply it by 3. So I also multiply 9 by 3. Similarly, to make 15 into a 30, I had to multiply by 2. That means I had to multiply negative 11 by 2. So we get 27 over 30 plus negative 22 over 30. Of course, this is 27 minus 22 over 30. That's just 5 over 30. And that happens to simplify. 5 does go into 30 6 times. And we're left with 1/6. Here we have 1/2 plus 1/4 plus 1/8. This is a harder problem because it's 3 fractions, but I'm not going to go through all the steps and details. I want you to kind of do a little work as you're watching. You'll be able to discover, if you did like I did with all the rest of the problem, that the LCD is actually going to equal 8. So I'm going to turn everything into fractions that are over 8. But I don't have to, the last fraction is just going to be the same. Now, in order to change 1/2 to something over 8, I would have had to multiply the 2 by 4. So I have to multiply the 1 by 4. Similarly, 4 times 2 equals 8, so I have to multiply the numerator by 2. And that looks like we have 4/8 plus 2/8 plus 1/8. And for fractions like this, you just add them all up. 4 plus 2 plus 1. The whole thing over 8. And that is 7/8. Now we can do some algebraic type problems. These are all the ones that have numbers in them. Now what happens when you see something of this nature? 8 over d plus 3 over 7. Now you've got a letter that you can't possibly break down into prime numbers, no matter what you do. So the best thing you can do is the following. What I can do is determine that the LCD, I'm just going to multiply the two denominators together and get 7d. So that means I'm going to change both denominators to 7 times d. So that means for this first fraction, I didn't multiply by d, but I multiplied by 7. 8 times 7. For the second fraction, I already had a 7, but I need a 7d. So I had to multiply by a d, so I have 3d. So if you look at this, if I cancel the 7s, I have 8 over d like I started with. If I cancel the d's, I do get the 3 over 7. So there's still the same thing. I mean, this is following the rules like it's supposed to. Then I'll have 56 over 7d plus 3d over 7d. Add them together, and I get 56 plus 3d over 7d. And there's no way to simplify this. If this were a multiplication symbol, I might be able to simplify, but in fact it is not. So there is nothing that I can do. You can't really cancel across an addition sign. Next I have 1/4 minus 10 over 11. Now both 4 and 11 are prime numbers. 4 is not a prime number, sorry. 4 equals 2 to the second. 11 equals 11 to the 1. I can't really do much with 11 because it's a prime number. Here then, I'm going to get a 2 and 11. I'll need a 2 to the second. So I will do this over 44. For the 4, I had to multiply by 11, so I will get an 11 in the numerator. And over here, I had to multiply by 4, so I will get a 40 in the numerator. And it looks like I get negative 29 over 44. Next, I have 7 halves plus 1 over 5n. Well, once again, 2 and 5 are prime numbers. So the LCD will be 2 to the 1 times 5 to the 1. But you're also going to have an n. There's nothing I can do about it. But the number parts I can get by the process I used earlier. So this is equal to 10n. So what I'm going to do is I'm going to change each fraction to being over 10n. Let's start with the 7 halves. That 2, in order to make it a 10, I had to multiply by 5, but then there was an n attached. So I have to take 7 times 5n. And over here, to make 5n into a 10n, I simply have to multiply by a 2. And so I get 35n over 10n plus 2 over 10n. And it looks like I'm going to have 35n plus 2. Let me increase that division bar. And there you go. What do we have next? I have w over 8 plus 5 over 6. And now, for LCDs, I'm going to let you work them yourself, but I will tell you what they are. In this case, the LCD is going to equal 24. You can do that by the process that I've shown you. So I'm going to write each of these fractions as being over 24. In order to make 8 into a 24, I have to multiply by 3. So I'll get a 3w. In order to turn a 6 into a 24, I have to multiply by 4. So I get a 20. So I get 3w plus 20 over 24. Next, I have 3 over y squared plus 10 over y. And you can treat this just like any of the other ones here. The LCD this time, if I want something that goes into both of these things evenly, I'm talking about the y's, then I only need y to the second power, because y to the first fraction's denominator, y to the second will go into it, and y goes into y squared as well. So what I'm going to do is rewrite my fractions to have y squared in the denominator. The first fraction I didn't have to do anything, but the second one, in order to turn a y into a y squared, I had to multiply by y. So I get 10y. And then when I add them together then, 3 plus 10y all over y squared. Now I'm going to do several more examples, but I'm not going to go through the effort of spelling out the LCD. I'm going to leave it to you to do while you're watching the video. Let's go with the next one here. A lot of times you can tell what the LCD is pretty easily. And I'll tell you, in this case, the LCD equals 24. And so I will want both of my fractions to be over 24. Starting with the first one, in order to change 8 into a 24, I had to multiply by 3. So for this first fraction, I'll get 7 times 3. For the second one, in order to turn 12 into a 24, I had to multiply by 2. So I get 21 over 24 minus 10 over 24, and that equals 11 over 24. Next, I have negative 7/12 minus 2 over 7. LCD equals 84. I'll let you check that yourself. Now, I think it's useful if I put the negative attached to the numerator when I'm doing this kind of stuff. 12 goes into 84 7 times. 12 times 7 is 84. So I have to multiply the numerator by 7 as well. Similarly, I'm going to sneak the negative up into the numerator of the second fraction. 7 goes into 84 12 times, so I had to multiply 7 by 12, so I'm going to multiply that 2 also by 12. So I have negative 49 over 84 plus negative 24 over 84. Negative 49 plus negative 24, I believe, is negative 73. And we're done. Next, I have 7 over 20 plus 12 over 35. I'm going to do the LCD here. And you can do this. I'm only going to put these numbers so that you can check them. And you should be able to check that on your own later on. So each one of these I'm going to rewrite as over 140. And I'll figure out what goes into those numbers. So 20 goes into 147 times. So I have to multiply the numerator by 7. 35 goes into 144 times. So I have to multiply the numerator by 4. So we have 49 over 140 plus 48 over 140. That equals 97 over 140. Now I know it's done. I just happen to know that 97 is a prime number. So you're not going to be able to cancel anything because nothing will go into 97. Let me show you something that you learned in school years ago. Usually when you were in elementary school, they would say, take that thing and turn it into an improper fraction. So convert you may or may not remember all the details, but you should probably remember it looked like this. 3 1/8 was equal to, now what happened is it's over 8, but the way it worked is you did 3 times 8, so I did 3 times 8, and then you added the 1. So 3 times 8 is equal to 24, and then plus 1 is 25 over 8. So that would be your answer. That would be taking a mixed number and converting it into an improper fraction. However, I'm going to use this as an example. Did you know that 3 1/8 is the same as 3 plus 1/8? they just, all these years, they have simply suppressed the addition sign, and you may or may not have realized. I think most people do realize there's a plus in there, but if you didn't, it is in there. So look at, if I do this problem as a problem like all the rest of them, what I would probably try to do is think of it as 3 over 1 plus 1/8. And then it's easy. The LCD is just going to be 8 because, well, since one denominator is 1 and the other one is 8, you only have to get both denominators to be the same as the 8. So I'm going to change this to an 8. Well, what do I have to multiply 1 by to give me an 8? I have to multiply it by 8. Now, before I do anything else, let me add this together. Let me come back to what I did up here. See this? Look at this. Do you see? 3 times 1 plus 8. 3 times 1 plus 8. All this was getting a common denominator of 8. That's all they've been doing for all these years, but they couldn't explain it quite like I did because they were dealing with kids. They didn't have time to go into all that detail, so they just left it at giving you the method and not really explaining how or why the method works. Just here's the method, do it. So this is 25 over 8, and there we go. You get this improper fraction. Whenever your fraction has a larger numerator than a denominator, it's called improper. Of course, we can do examples that are more complicated, like if I tried to do 2 plus r divided by 6, I would write that as 2 over 1 plus r divided by 6. And then my LCD would equal 6. Anytime one of the denominators is 1, the LCD is always easy to figure out. So what I have to do here, it's easy. Multiply 1 by 6 to make it into a 6. So I will multiply this 2 by 6. And I'll get 12 over 6 plus r over 6. And there's really not a lot of simplifying that I can do. I'll just do 12 plus r over 6. Next, we will do 1 minus 3/4. And I'll play the same game. I'll do 1 over 1. Which is 4 over 4 minus 3 over 4. And that equals 1/4. And then one last example. Here we'll do negative 4 plus x over 7. So I will rewrite that as this, and then that negative 4 over 1, I need to change it in 7. I had to multiply by 7, so that's negative 4 times 7. We have negative 28 over 7 plus x over 7. And so I get negative 28 plus x over 7. One last example that I want to do is a word problem. We're going to start doing more and more of those. This one comes out of your textbook. Let me make it a little bigger so it's easy to see it. This is problem number 74 from section 3.5. And what we have here is that the beginning of the school day, Lionel his laptop computer indicated his battery was charged to 7/8 capacity. Of course, as the day went on, his battery was drained, and by the end of the day, he only had 1/3 capacity left. So how much battery did he use in the meantime? Basically, all we're trying to do is, he started with 7/8. That was my start. And he ended with 1/3. And we would like to know what that equals. So I need an LCD. Once again, I'll let you figure that out. So I'm going to rewrite both of these fractions over 24. Well, 8 times 3 is 24, so I had to multiply the 7 by 3. Similarly, 3 times 8 is 24, so I have to multiply the 1 by 8. And we get 21 over 24 minus 8 over 24. And that equals 13 over 24. So that's how much battery he used in the day.